So let us take up a problem where we will calculate that what is the distance between 2 points whose intensity is 2 I naught. This is 2 I naught, 2 I naught. This is 4 I naught. So we are interested to calculate this width, that is the half intensity width of interference pattern. Let us call this distance as y, and now we have to relate this y with intensity. That means the intensity should be here 2 I naught. So now we have our formula that intensity will be 4 I naught cos square phi by 2. Now at this is intensity at general point whose phase difference is phi. So here I want 2 I naught intensities. So 2 I naught is 4 I naught cos square phi by 2 implies cos square phi by 2 as 2 I naught by 4 I naught is half, implies cos phi by 2 is equal to 1 by root 2. Cos phi by 2 is 1 by root 2. So we have phi by 2 is equal to, that is 45 degree pi by 4, implies this becomes pi by 2. So whenever the phase difference becomes pi by 2, 3 pi by 2, we will have intensity as 2 I naught. So at these locations I require my phase difference to be pi by 2. So let us now see at what value of y I will get that. Now we know that the path difference delta x is created because of this y is equal to y small d by capital D, and this path difference has a corresponding phase difference phi as 2 pi by lambda into delta x. So we will put this here. So hence implies phi will be equal to 2 pi by lambda into y d by capital D. We will call this 1, this call it 2. This is phi. Now we will equate this. So from 1 and 2, from 1 and 2 we get pi by 2 is 2 pi by lambda y d by d. So this pi cancels. So we get y is equal to lambda d by 4d. That is lambda d by d is beta by 4. So at beta by 4, beta by 2 you will have darkness. This distance is beta by 2. So beta by 4 means half of this, at the center you will have 2 I naught. So this total distance, that is delta y, that is the distance by which these 2 is separated, will be 2 times beta by 4, that is beta by 2. So thus with the help of this problem we have seen that we can calculate at any general value of y what will be the intensity. So the most important point which we have to learn from this problem is how to relate the path difference with y. If I move y distance from the location of central maxima, then how much with y path difference will be created, how much path difference is required to create the phase difference, and once a phase difference is created, then how much will be the intensity. So these two terms are very important. Now next we will see that on the screen how many maximas and minima will be formed, how many fringes will be formed, and how to locate the central maxima also. Because you see, since all the fringes look same, so where is the central maxima is very difficult to arrive. So how we will do, let us see. Now let us see in a YDC experiment on the screen how many total number of interference pattern can be formed. So this one is my S1 and this much S2, and I call the distance between, this is the standard terminology we will use, the distance between S1 and S2 to be D, and on the screen we will have this D. So here on both side, on the upper side and on the lower side, we will have maxima. So total number of maxima we are interested in, including central maxima. So suppose I take a point P, then the path difference is given as d sin theta, where theta is the angular position of P. So now for constructive interference, interference, we have path difference d is equal to n lambda. When n is 0, you will get a maxima. When n is equal to 1 means lambda path difference, you will get a maxima. When n is equal to 2, so n can have any value. So n will give the number of maximas possible. Now here sin theta will be equal to n lambda by d. Now we have sin theta always less equal to 1. Always less equal to 1. Minus 1, it will be greater than minus 1. We are interested in greater equal to 1. So n lambda by d is less equal to 1, implies n is less equal to d by lambda. Now n will have integral values, so we will write, so total number of fringe, total number of bright fringe on the screen will be equal to, suppose this is 5.5. 5.5 means I can have only 5 bright fringes. 0.5 bright fringe has no meaning. So we will have 2 times greatest integer function d by lambda, means whatever the integral value of d by lambda will be there, lesser than d by lambda, that is called in mathematical language greatest integer function. 2 times this, because up and down both will be there, 2 will be there, and including the central maxima, we will have 2 greatest integer function d by lambda plus 1. This is the total number of fringes that will be formed on the screen in a YDC experiment. Now let us see how to locate a central maxima. So central maxima is a point where the two waves interfere with a 0 path difference. Now suppose I use a monochromatic light, then the intensity pattern will be like this, and the whole screen will look alike. So if we concentrate here, it will be very difficult to locate what is the location of the central maxima. So in that case, what we do, we use white light. White light is not monochromatic light. What happens actually, when we use white light, we get interference pattern, the superposition of interference pattern of all lights. So this is the location where the maxima of all the lights will fall. So the central maxima will be white. In that case, central maxima will be white. What will happen? White light has a distribution from violet to red. Red has, suppose it has 3000 angstrom, 3000, 4000 something, this is 7000 angstrom wavelength. So beta, since beta depends on yd by d, that is lambda, so more the wavelength, more will the fringe width. So you see here you will get brightness of all the lights, and suppose here this is red brightness of red light. So violet, you will get violet brightness here. That means on the screen there will be different colors, somewhere red, blue, green, everywhere the whole screen appears to be colored. There will be some darkness somewhere if the darkness of all overlap. So the whole region on the screen appears to be colored, but the central maxima will be white. So in this way, if we use white light, then we can locate the central maxima of the experiment. Once central maxima of that equipment or that screen is located, then we can use another monochromatic light to study all such things. So in this way, white light is used to locate central maxima. So now let us take up a problem of a modified YDS experiment. This is my source, and here the light is a spherical wavefront which is incident obliquely. It is not a normal incidence. So when it is not a normal incidence, let us see what will happen. So this path S1 to S is given as length L1, and this is S2, this length has L2. So this source is located in such a way that this path is L1 and this path is L2. This is D, and the screen is placed at a distance L. So number 1 point we have to find it, how many fringes are formed on the screen. How many fringes are formed on the screen? Fringe and location, we will locate location of central maxima. And third, what is the fringe width? Let us calculate these three things. So now this is the problems, three problems. We have to see where is the central maxima, what is the fringe width, and how many maximas are there if there is an oblique incidence. Now number 1 point, let us calculate in reverse order. We will do first third problem, second, then first. Fringe width calculation. You see, fringe width calculation has nothing to do with whether the wavefront is incident normally or obliquely. Fringe width is always given as beta is equal to lambda d by d. So this is not going to change. In my case, beta will be equal to, this is lambda, d means L by d. So fringe width has nothing to do with whether the source is giving an oblique incidence on S1, S2 or a direct plane wavefront is given. So in all the cases, my fringe width is lambda given by beta is equal to lambda d by d. So this is over. Now location of central maxima is tricky, because this time when the central maxima will not be at the geometrical point, this geometrical axis here, because these two waves from S1 to S2, these paths are same, but here there is a difference. So now let us see that where is the central maxima located and how many fringes will be formed on the screen. Let us see it. Now let us see that where is the central maxima located and how many fringes will be formed on this. In order to know that, let us take a general point P, which is at an angle theta. So at P, the geometrical path difference becomes d sin theta. So you see this path and this path. The total path difference here is due to path difference here and here. So, what is the path difference created here? This is L2 minus L1 this term, and this is d sin theta. Now, for any point P, you see whatever P vary, wherever the P varies, this L2 minus L1 does not change, only d sin theta changes. So, for maxima, for constructive interference or maxima, this L2 minus L1 plus d sin theta is equal to n lambda. So, we can have sin theta is equal to n lambda minus L2 minus L1 by d, this expression. Now, let us first locate where is the central maxima. At central maxima, we have path difference 0, path difference equal to 0. So, n lambda, this delta x is equal to 0 means n lambda, i.e. n is equal to 0, n lambda is 0. So, moment this is 0, then we will write sin theta naught, location of central maxima is theta naught, is equal to this is 0. So, it becomes L1 minus L2 by d. L1 minus L2, you see this L2 is in my diagram more. So, L1 minus L2 implies that my theta as shown in the figure is going to be negative 1. That means my central maxima will not be this way, my central maxima will be this way. Thus, the angular position is given by this. This is the angular position of this, which is formed this way. So, the central maxima will be below, let us call it O. By what angle? Sin theta naught equal to this. This is the location of central maxima. Now, in order to know how many maximas will be there in the entire screen, we will use this inequality. The expression of sin theta is less equal, sin theta value is between minus 1 to 1. So, we will use this. So, we will get sin theta, that is n lambda minus L2 minus L1 by d is less equal to minus 1 to 1. That means when I use this value, we will get one thing. When I will use this value, I will get one thing. Let us do that. So, now you see when we got this, just transposing all this term, we will get n is less than this and n will be less than this. So, n will be less than this and there will be two inequalities, one part this part, one part this. So, n max we can calculate by calculating this, and n min we can get by calculating this inequality is there, minus d plus L2 minus L1 by lambda. So, let us see the total number of fringes, how much total fringes will be formed on the screen. The total number of fringes formed on the screen is equal to, this is n max minus n min plus 1. See, here there are some fringes and here, and there will be somewhere here the central maxima. So, if I calculate, suppose the fringes here, the order will be negative. That means suppose here I have minus 15. That means the nth order of the fringe minimum is minus 15 and the maximum fringe suppose here I got is 10. So, if I want to know how many fringes are there, so this is 15 order, this is 10 order, and somewhere central maxima will be Zeroth order. Zeroth order is not calculated in n max or n min. So in order to know the total spread of fringe edge, we have to use n max 10 minus n min, that is 10 minus 15, that will give you 25, and then plus 1. That means plus 1 here is for central maxima. So the total number of fringes will be this, which from here we can say that it is 2d by lambda plus 1. So here we have seen that if the incidence is oblique, then on the screen beta, the fringe width does not change, the central maxima shifts to this position, and the total number of fringes is 2d by lambda plus 1, which was as if it is a normal incidence. Simply about this point the number of fringes will be changing. So in this problem we have seen. Now let us see what happens to the fringe edge if we place a dielectric slab in front of one of the slits. So that is the fringe edge will shift. Let us see how the fringe edge will shift on inserting a dielectric in front of one of the slits. So now let us learn the fringe shift due to a dielectric medium in front of one of the slit in YDSC experiment. That is, dielectric medium is a slit here, slit. Now suppose this is a dielectric slab of thickness T and has a refractive index N. So suppose a light wave is incident on it. Suppose a light is allowed to pass through here and it is allowed to pass in air just like this. So if this is T, the optical path length of this is equal to NT. That means if a photon or a light wave comes from here, the moment it just comes out from here, that light wave reaches in air or in vacuum this distance. That means the additional distance, this is the additional path difference created between this wave and this wave. So this, thus a dielectric substance produces an optical path difference. Now how much will be the path difference? So the path difference created by the dielectric slab delta x will be equal to this distance n into t. N is, this is the optical path length of this, minus t, that is equal to t n minus 1. This is the path difference created by a dielectric slab. Now once I know the path difference, the effect of a dielectric slab on the path difference created, now we can predict how the fringe will shift in a YDSC. Now let us see this. Now this is my YDSC setup. This is slit S1 and this is slit S2, and in front of this slit S1 I have placed a dielectric slab of thickness T and refractive index mu or n, anything we can assume it. Now what happens? Suppose this is a point P. Now what is this point P? I want to locate central maxima, that is the point where the path difference between the waves arriving from S1 and S2 is 0. So what happens? By moving this distance y, we have created a geometrical path difference between S2P and S1P. So if this additional geometrical path difference compensates for the path difference created by this dielectric slab, then at P I will get a maxima. So the path, the fringe width, first of all the fringe width does not change when we insert a dielectric slab. Fringe width beta is constant. Beta does not change. What is changing is the whole pattern, the shift in the pattern. The central maxima shifts here upward. The central maxima simply shifts in such a way that the geometrical path difference created compensates the path difference created by the dielectric slab. What is the geometrical path difference created if I move y distance? The expression is y d by d is the geometrical path difference created if I move y distance. Now, if this is compensating this path difference, that is t mu minus 1, then this path difference, geometrical path difference, is compensating this path difference. In that case, y becomes t mu minus 1 d by d. Thus, this is the distance the central maxima shifts when a dielectric slab is introduced in between one of the slits. This is the distance it's. Now, if I introduce one more slab here, then the shift due to this one is y1 and the shift due to that will be y2. So, total shift will be added. Y will become y1 plus y2. One more thing, if I place one more slit here, then this slit will try to bring this shift downward. That means the shifts has to be algebraically added. So, we may place another slit of different T1 and T2, mu1 and mu2. So, the net shift will be by the algebraic sum of the shifts. In this way, a dielectric will influence the fringe pattern. Now, let us take a problem that has already been asked in IIT to illustrate this idea. Now, let us see a problem which appeared in IIT. Match the following is there. We have two columns, column 1 and column 2. So, column 1 shows 4 situations of standard Young's double slit arrangement with the screen placed far away from the slits S1 and S2. In each of these cases, S1 P naught is equal to S2 P naught. S1 P1 minus S2 P1 is given lambda by 4 and S1 P2 minus S2 P2 is equal to lambda by 3, where lambda is the wavelength of the light used. In the case B, C and D, a transparent sheet of refractive index mu and thickness T is pasted on slit S2. The thickness of the sheets are different in different cases. The phase difference between waves reaching a point P on the screen from the two slits is denoted by delta P and the intensity by IP. Match each situation given in column 1 with the statements in column 2 valid for that situation. Now, next column 1 and column 2. So, in column 1 there are A, B, C, D entries and in column B 4 entries are there. So, this is, let us start with column A. So, we have in column A 4 different arrangements of Young's slit. Let us see one by one. So, suppose I start with A, the entry in column A. So, it is column A, we have S1 and S2 two slits, S1 and S2, S1 is here and S2 is here, and we have 3 points P1, P naught, it is P1 and this is P2. So, what is given in the problem is S2 P naught is equal to S1 P naught. So, this S2 P naught is equal to S1 P naught. In the problem, let us see reverse. That is given S1 P1 minus S2 P1 is equal to lambda by 4. Also given is S1 P2 minus S2 P2 is equal to lambda by 3. So, what is given in the problem is this is a YDAC setup. S1 and S2 are 2 slits, P0, P1, P2 are 3 points on the screen, and here the path difference is 0, means it's a source of central maxima might be here. Here the path difference is lambda by 3, and as you go here the path difference becomes lambda by 3, here it is lambda by 4. So, now we have to calculate, we have to see what is the path difference here. First of all, let us see for the path difference. Now, the path difference at P0 is equal to 0 because these two are 0. They are of equal length. So, path difference and phase difference. This is phase difference. Phase difference is denoted as lambda P and intensity is denoted as IP. So, this is what we have to calculate. We have to predict phase difference and intensity at P0, P1, P2 in different situations in column ABCD. This is our problem. So, the phase difference is here 0 because the path difference is 0. So, option A. So, let us see that option A here path difference is 0. So, P0 will be equal to 0. So, that is option P because here path difference is 0. About P1, option B is path difference at P1 is equal to 0, that won't match. P1, that is the intensity at P1, that is here intensity at P0 will be equal to 4 I0. If I0 is the intensity somewhere here, I0 and I0 is the intensity. So, P0 intensity will be here 4 I0. What about intensity at 1 and 2? You see here there is a maxima that is 4 I0 and the path difference will be here as we go on. The path difference somewhere will become here lambda by 2. So, when the path difference becomes lambda by 2, here you will get minima, but here this is lambda by 3 and lambda by 4. So, lambda by 2 means 0.5 lambda, this is less than this and this is less than. That means as you go away the intensity decreases. So, for this case I will say that the intensity of P1 is greater than intensity of P2. Let us see whether this option is there na? Intensity of P1 is greater than and intensity of P0 is further greater. So, option 1 I is not there, P1 intensity of P1 is equal to 0, that is wrong. Then option R, intensity of P0 is greater than P1, that is correct. So, here R option will be there, and T option, intensity of P2 is greater than, that is wrong. So, for A, for this only P and R is the correct option. So, A matches with P and R. P means what is option P? P option tells that the intensity here phase difference is 0 and R option tells that intensity of this is maximum. So, you see the intensity profile will be something like this. So, here the maximum intensity, and as you go on, this is path difference lambda by 2, this is minima, intensity decreases. So, this is for A option. Now, let us see option B. So, in option B, in the slits, this is P naught, this is again P1 and P2. In front of the slits, some dielectric slab is introduced. In option B, we can see some dielectric slab is introduced. The dielectric slab is such that mu minus 1 T is equal to lambda by 4. That means the path difference created by this is here. Now at location of P2, we see that the path difference created is lambda by 4. This path is longer than this path by lambda by 4, and again a delay is created. That means if then this will be the location of central maxima, because the path difference created by this slit is compensated by the geometrical path difference created at P2. So here will be the central maxima, and this is the central maxima. So somewhere you will get more intensity like that. So this is the intensity profile going like that. So now the options, option A, P naught, A becomes A cannot be matched with P because path difference is 0, not at P naught but at P2. So P does not match. Path difference as P1 is 0, that is also wrong. Path difference at 1, it is sorry, it's not talking about path difference. Now I option, R option and T option is talking about the intensities. So intensity at 1 is 0, it's false because it's not a minima. Intensity of P naught is greater than P1. This is also wrong because as you go on this is the central maxima. As you go on, the intensity of P naught decreases. So it is a maximum intensity and it decreases like this. So R option is wrong. What about T? Intensity at P2 point is more than P1. Of course, here it is as a maximum. So A matches with last option T. Sorry, not A, B. B, this is the B. B matches with T option. So now come to option C. So in C, we have again mu minus same figure, but simply mu minus 1 T is equal to here lambda by 2. This is lambda by 2. So the whole, now let us see about C. So if it is same diagram I have to use, but this time this is lambda by 2. Now mu minus 1 T is equal to lambda by 2. So now let us calculate that this is lambda by 2. So at what location we will have a maxima? So you see, if this slit is not there, here the path difference is equal to 0, and here somewhere we were getting a minima. So the intensity profile was something like that. But now if I introduce this a path difference lambda by 2, here the path difference is lambda by 2. That means at this location now there will be central maxima. So what was the previous first minima is now the central maxima. So my intensity profile simply changes. This is the maximum and this is the minimum. So my intensity profile changes like this. Here I will get now the maximum 4 I naught, and here I will get 0. So what about option P? So the phase difference at P naught is 0. So this C, so here the path difference due to this is compensated and the phase difference is not 0. Here the central maxima phase difference is 0. So P is wrong. Option Q, at P1 the phase difference is 0. That is also wrong. Intensity at 1 is 0. That is not correct. You can see this is the intensity profile, and intensity at P naught is less than, intensity at P naught is greater than P1. That is also wrong. Last option, the intensity of P2, this is P2 is greater than intensity of 1. This is correct. So the last option C matches with C, T. So you see how beautifully the IIT has asked that how the central maxima and the path difference will change by introducing a dielectric slab in the medium. Now you see here P1 has a path difference lambda by 3, P2 has a path difference lambda by, this is lambda by 4 and this is lambda by 3. Now here the dielectric slab is given in such a way that the path difference created is 3 lambda by 4, that is 0.75 lambda. So that means the central maxima will shift. Here path difference is 0.25 lambda, 0.33 lambda. So here path difference, so central maxima will be somewhere here, and here the path difference is lambda by 4, here the path difference is 3 lambda by 4. So this path difference is lambda by 2 between these 2 points. That is why there will be a minima here and there will be a maxima here. So now the options is first option, let us see D, means first option P naught. At P naught the phase difference is 0, that is wrong. At this point we will have a phase difference 0. Next at P1 the phase difference is 0, that is absolutely wrong. At P1 the phase difference is pi, so PQ option is not there. Now I option, that is intensity at 1 is 0, so that is correct. Here at intensity at 1 is 0, so D matches with the option I. Next option about R, that intensity of P naught is greater than P naught, P1. So you see again the next will be like this. So P naught has a more intensity, so that option R is also correct. Next T, P2 is greater than intensity. So you can see P2 has greater than intensity. So this option is also correct. So D has these 3 options. So these ABCD options matches in this following manner.